So under the framework of the consequences of the Riemann-Roch theorem, as I stated in the previous video, first we see that all divisors which has dimension G. So of course we suppose that we are given a function field of genus G. And we will see that in the all divisors is of dimension G and is of degree 2G minus 2 is as canonical divisor. And the first part the necessary part is coming from the proof of the uniqueness, or the proof of Riemann-Roch theorem. And for the sufficient part, we suppose that we are given a divisor is of dimension D and degree 2G minus 2. And like in the uniqueness of the divisor, similarly we consider divisor W minus D. This is the canonical divisor in the Riemann-Roch theorem. And this is of dimension, this is of degree 0, because we suppose that the divisor B has degree 2G minus 2, and we also know that degree of the canonical divisor is 2G minus 2. And on the other hand, by the Riemann-Roch theorem, we also know that its dimension is equal to its degree plus 1 minus G plus L minus B. And by the assumption, this is G, this is 2G minus 2, and this shows us it is of dimension 1. And we also know that the degree, in this case, if it has dimension 1, we can characterize the degree 0 divisors as principal. And W minus B is principal. And this shows us indeed B is equivalent to B. So B is a canonical divisor. And now indeed, as a weaker version of the Riemann-Roch theorem, we can present Riemann's theorem. Indeed, we will see that if we are given a function field of genus G, and if the degree of a divisor is sufficiently large and this quantity is determined by the 2G minus 1, then the dimension of a space is equal to its degree plus 1 minus G. And it will be often used in the computation aspect. Particularly, we will use it in algebraic coding theory when we want to determine the parameters of the linear codes. So by Riemann-Roch theorem, we know that it holds for every divisors plus 1 minus G plus N W minus A. And if degree is bigger than or equal to 2g minus 1, and degree W is equal to, the degree of the canonical divisor is equal to 2g minus 2. Degree of the W minus A is negative in this case, so that means this is a trivial space, so is of dimension 0. And this allows us to compute the dimension of the divisor exactly. And actually, I mean, at the moment, it's not so that clear how the genus affects and the divisor, the canonical divisor affects, or the dimension of the divisors affect to each other. But at the moment, let me just briefly explain what genus tells us, or what kind of examples do we have. And for this purpose, first, let me consider the rational function field. And indeed, we will see that it has genus 0 and it exists, it contains degree 1 divisor. So first, let me suppose that we have a rational function field, which is determined by its some transcendental x. And to see that the existence of the degree 1 divisor, it will be enough to consider the rational place P infinity. That means the pole divisor of x, because we know that this is a rational place, and this shows us the existence of such a divisor. And now we want to see that it has genus 0. And in order to see that, first let me consider the Riemann-Roch space NP infinity for a positive, with a positive integer m. And we also know that it contains n plus 1 linearly independent functions over k. Linearly independent functions over k. So in this case, its dimension, I mean, if it contains n plus 1 linearly independent functions, its dimension is bounded below n plus 1. On the other hand, if m is large enough, so for instance, if m is bigger than 2g minus 2, by the consequences, we know that its dimension is equal to its degree plus 1 minus g. So n plus 1 minus g. And we know that, in this case, we can observe that g is less than or equal to 0. On the other hand, we know that genus is also positive integer, and this forces the rational function field is of genus 0. To see the sufficient condition, let me suppose that we are given a function field with genus 0, and we know that there exists a degree 1 divisor. And in this case, let me observe that degree A is bigger than or equal to 2g minus 1. Because in this case, 1 is always bigger than is minus 1. And by the consequence of the Riemann-Roch theorem, thanks to this condition, we can see that it has dimension degree A plus 1 minus G. And by the assumption, we know that the genus is 0 and degree is 1. In this case, this is of dimension 2. And by remark 1, 5, 17. So in this case, if it has dimension 2, as we have also considered in the discussion session, we know the existence of a positive divisor, which is equivalent to A. So by the equivalence, that means they have the same degree and they have the same dimension. So thanks to this dimension, we can guarantee that there exists a transcendental element in its associated Riemann-Roch space. So that means if you consider its principal divisor, it's going to be non-zero. And since it is an element in the A space of the A prime, we know that its zero divisor minus principal divisor is bigger than or equal to minus A prime. So this A prime is a positive divisor. Its degree is 1. As we have in the discussion session, this is possible only when A prime is the principal divisor of X. Then now, if you consider the extension of F over Q of X, by theorem 1.5.11, we know that this extension degree is determined by the degree of the principal divisor, and by the assumption, thanks to equality A prime and the principal divisor of X infinity, indeed we see that it is 1. And this shows that any function field with genus 0 and that contains degree 1 divisor is a rational function field. However, at this point, it's worth to point out that so this gives us the characterization, this proposition gives us the characterization of the rational function field. But to conclude that a function field is rational, it's not enough to have a genus 0. Indeed, later we will see that there exist non-rational function fields of genus 0. So actually, thanks to this proposition 1.6.3, so that means such function fields does not contain any degree 1 divisors. For instance, as a counterexample, later we will prove in the exercise 1.10 the function field, which is an extension over the rational function field with constant field real numbers, is of degree 2 and determined by the irreducible polynomial t squared plus x squared plus 1. Is of genus 0. At the moment, this is not so clear. But this is not rational, and we will see it later. All divisors is of degree 2. So this is a counterexample of this case. On the other hand, if our base field or full constant field is algebraically closed, if K is algebraically closed, we know that all places are rational. Are rational. So that means all places are has degree 1. And this shows us the existence of the degree 1 divisor. And in this case, it will be enough to characterize only by looking at the genus of a function field. And it's worth to keep in mind, but it's it is explained in the advanced topics, like in chapter 5. Indeed, if our base field is a finite field, later we will see that the existence of a degree 1 divisor, again, in this case, the genus will be enough to characterize a function field, if it is rational or not. And I think at this point, it's worth to consider the rational function fields again, and to go over the notions we have seen so far over this simplest example.